Thank you. Okay, so what I want to talk to you about today, you could call something like the cognitive control of learning. And the basic motivation, I think, is basically motivation behind this workshop, which is that learning underlies so much of our behavior, and learning takes time. Time is precious, and there's always going to be a huge premium in our lifespan on learning rapidly. And what we choose to learn during our lifespan also ultimately, accumulates to, in part, to who we are. And so I think this process is very important to study. And the smaller version of that I'll address in this talk is, do biological organisms think about themselves as learning agents and maybe modify their behavior in order to learn better? So what I'll talk about is how rats learn a visual object recognition paradigm. And then I'll talk about a neural network theory of how sort of short-term decisions influence long-term learning. And then close with some additional experiments once we had that theory that tried to see if this might be what's going on in the rodent behavior. So imagine you're, for instance, chopping vegetables. When you do this, you face a delicate choice. You could chop this bell pepper very quickly, but then you might cut yourself. Or you could chop it very slowly, you'd be very accurate, but you wouldn't get many slices out per unit time. And this is the standard speed accuracy trade-off, where your initial response time, if you take a long time to respond, you'll get a high accuracy on the task you're interested in, but you'll also get potentially a low reward rate because you're taking a long time to make each decision. Now, you could also do this same task for a very, very long time and become expert at it. And the question that I'm interested in here is basically, how does this speed accuracy trade-off shift over learning, and how do agents navigate it? So you might imagine a novice is going to have some trade-off, but if they invest enough time in a task, they can completely reconfigure that trade-off and it may be beneficial to them. So how do agents learn this speed accuracy trade-off? To get some experimental purchase on this, Javier, who's the workshop organizer here, did a bunch of high throughput visual object recognition training with rodents. And the task, basically we have an animal. It's going to get 3 lick ports. It licks an initial lick port to initiate a trial. There's a computer screen in front of it. We display one of 2 complex objects that can be rotated and turned around. So it's actually a very complex recognition task that the animals are performing. And then the rat makes its choice by picking a side, and we start the next trial. So that's the task. And the thing is, even in this task, you have an option here. You can stare longer at the stimulus to try to get a better sense of what it is, or you could guess really quickly, just randomly guess. These are all strategies the animal has access to. And the classic way of modeling this, and we have to go through it to sort of explain how I'm going to present the data, is a drift diffusion model. And so here, basically, we imagine that there's some underlying decision variable. And over time, that decision variable is going to fluctuate noisily during a trial. And then at some point, it's going to hit one of these 2 thresholds, and that will determine the animal's choice. And you can see that which threshold it hits determines what the choice is, but there's also the time it takes for this process to hit a threshold, and that determines the reaction time. And how good an animal is at the moment is going to depend on how much coherent drift there is towards the correct boundary as opposed to the other boundary. So that's the signal to noise ratio. So you can imagine that could change over time. So you're on average moving faster towards the boundary. And that also will impact your decision time. And then this model has been used to, for instance, look at the reaction time distribution and many other properties of behavior. All right, now there's one other thing I have to tell you about the drift diffusion model, which is a remarkable mathematical fact. And that's that it allows you to solve the optimal speed accuracy performance in this task, and it has a particularly clean solution here. So we can plot things in speed accuracy space now. On the x-axis, we have the error rate. On the y-axis, we have decision time. And so, for instance, if an animal is over here getting very few errors, it's probably got a very large SNR, coherent drift. And also the reward rate is increasing. If you come down here, this means you're going quickly and you're making very few errors. So that's just to orient you to the space. And now as an animal, if you have some fixed level of SNR, so the ability that you can perceive the stimulus, you can choose lots of different thresholds. And that influences how long you'll wait and your error rate. And so for a given SNR, you lie somewhere on this curve, which is a performance frontier for your current SNR level. And as you get better, you could have lots of these different performance frontiers, and you have to choose where you want to sit on this by adjusting your threshold. Now, the remarkable fact is that if you adjust your threshold optimally, you have to lie on this optimal performance curve. And so what that means is, for all of these cases, what you should be doing is locating the speed accuracy trade-off on this black curve here. Okay. And just again, the intuition, basically, if you're really accurate, what should you do? Well, you should just go really quickly and rake it in. But also, if you're really inaccurate, you should also just guess, because waiting longer is not going to help you. So this is a fast guessing strategy. And then it's sort of in the middle regime, it's some trade-off there. All right. So how does rat behavior evolve over learning? Well, what we see is a very interesting pattern, I think. Here's a cohort of rats and their average behavior plotted in speed accuracy space. The dark means the beginning of training, and the lighter colors are the end of training. And this is actually many sessions. So it's, so we're talking about long-term learning here. And what you can see is that there's actually this large deviation from optimality initially in learning. But then after the learning process, they're getting reasonably close to the optimal point on the speed accuracy curve. And to quantify this, one thing we can do is look at basically how much they're giving up given their current behavior. So the rats that are up here, they could have been down here. How much reward rate are they giving up by being suboptimal here? And we can look at that through training. You see initially they're giving up, almost 20% of the reward they could be getting. And then by the end of it, they're actually getting almost all the reward they could. So that's sort of the overall learning trend. And the question that this prompts is basically what's going on here, right? Why give up so much reward initially in learning? So to get at this, we are going to look at a little model of this setting, a little theory. And we're going to imagine that basically the circuits responsible for this decision are a very simple recurrent neural network. And this recurrent neural network, basically, we're going to flip a coin, you get your stimulus, and you feed that to a network which has getting all of the pixels as its input, passes them through some synaptic weights W, which can be changed, and then it adds that into a decision variable that then propagates to the next time point, and you get a sequence of these images. And the idea kind of is that these images, they move around because the animal's eyes moving and maybe there's internal neural noise. And so it's beneficial to sort of get lots of views of the same object in order to make the decision. And at some point, this internal variable will hit a threshold and you make your decision. So hopefully you can see that this kind of looks like a drift diffusion model, except now we've got perceptual weights in here. This is a simple recurrent network, and we can ask what happens as you change those weights. Then at the end of the trial, you might be correct or not. And we can update the weights of this network just using standard gradient descent learning. What you'd do if you were just an engineer facing this task in a AI setting. All right, so this scheme that I told you, you could simulate this. You could simulate this model and see what behavior it generates. It turns out it's simple enough. You can also analyze its average dynamics. And in fact, it behaves exactly like a drift diffusion model, but with a time-dependent signal-to-noise ratio. So I won't go through this in detail, but the basic idea is this recurrent linear neural network can be redescribed, just changing the name basically to a simple drift diffusion model. That gives you correct and error trials. We're going to do gradient descent learning. But what we can do is calculate the average effect of gradient descent learning and express that instead as a change in SNR in this underlying DDM. And then that change in SNR will give us new performance in this linear network setting. And all of this is governed by a choice of threshold. But because we're investigating learning over many trials, the choice of threshold, we have to choose a whole function, right? At every trial, what threshold are we going to use? And those choices are, it's a short-term decision. What threshold do we use? It's going to impact the choice and decision time, but also it's going to impact long-term learning over many trials as we adjust the weights. All right, so here just to show you that this reduction is reasonably accurate. In blue, we have the average dynamics from this theory, and in gray, we have the simulations. And you can see that basically can describe all of the aspects of this particular simulation. I won't drag you through the equation, but this is the equation that actually pops out as the differential equation for the SNR. All right, so what do we get from that? Well, one thing that pops out if you look at that equation long enough is an interesting trade-off now between learning speed and reward rate. So earlier we were talking about decision speed and reward rate. Now we're talking about learning speed. And it's basically the same thing. If you go very quickly, then you're not going to learn very quickly because you don't get to see the stimulus long enough to know how to make an effective change. If you respond slowly, you will learn more rapidly on each trial, but the cost of that is your instantaneous reward rate will be much lower. So there's two speed accuracy trade-offs here, and one is on this long time scale of learning. All right, so in navigating that, we've seen how you can adjust the threshold to navigate the first speed accuracy trade-off, but how can you adopt different strategies to manipulate this longer time scale learning speed accuracy trade-off? And here we need a whole threshold policy that will tell you what you're going to do at each point in learning time. So we could consider different options. One option would be just greedily choose the reward rate, choose the threshold that maximizes instantaneous reward rate. Another option would be move towards the threshold that will maximize instantaneous reward rate, but start a little bit slow and then kind of drift towards it with an exponential relaxation. I'll call that immediate reward rate sensitive. And then finally, just to understand what would be globally optimal in this model, you can compute the oracle case if you were just trying to maximize total future reward over and including the learning period. So those are the three policies we can look at. And here's what they look like. If you are in this reward rate greedy, you have to always lie on the OPC. Right? That's what it means to be instantaneous reward rate optimal. So you'd be hugging the OPC the whole time. It turns out the globally optimal solution when you plot it in speed accuracy space is quite different. It actually starts incredibly slowly to harvest the benefits of learning rapidly. And then only at the end sort of comes in towards the OPC. And this IRR sensitive policy sort of splits the difference between these. And of course, we think it's reminiscent of what the rodents are doing in this task. So basically, there's this trade-off where in the greedy case, you're maximizing your instantaneous reward rate at any point in time. And in this globally optimal case, you're maximizing the total future reward. And then, somewhere in the middle is the policy that we seem to see adopted in practice. Now, what does this mean in terms of their total reward behavior? Well, at the level of instantaneous reward rate, we can plot this and for the model and these different threshold policies, and it kind of behaves, I think, as you'd expect. So if you greedily act, then you're collecting higher reward rate initially, but you're not getting to a higher reward rate later on, and that can be quite slow. So you see there's actually this long plateau with the greedy strategy where you just don't learn anything before you finally pop up to learning more about the task. And if you zoom in, you can see that initially you are better off the greedy strategy, but this quickly flips. So we think this is maybe why you'd want to adopt this other strategy. And if you look, the difference between this IRR sensitive strategy and the global strategy is actually not so big in this case. So I think that the IRR sensitive strategy is actually getting quite close to the global optimal strategy. Okay, so that's some high level theory, but can we test some of the hypotheses that would flow for this? I mean, you could probably create many theories that would have been consistent with the rodent behavior here. And I'm still not sure we've fully pinned it down, but here's some of the ways that we tried to test this. So the first thing we want to test is this idea that learning speed is related to how long you look. And so to do that, we can say, make some simple predictions. If you respond slowly, then we predict you should learn faster, right? If you respond slowly, we predict you should eventually get to a higher instantaneous reward rate. You should have a crossover in the instantaneous reward rate if this is a beneficial thing to do. And if you respond slowly, this should ultimately mean you accumulate a greater total reward. So Javier sought to test this by doing new experiments where we manipulate reaction times. So what we did, we took the animals, we randomly split them into two groups, and then we basically forced them to respond above or below their mean RT. So we have them grouped into a slow group and a fast group. And then we can check these predictions here while they learn this new stimulus mapping. And what we see is indeed the animals that we forced to go more slowly learned faster. And this is, of course, what's predicted by the model as well. Okay, and additionally, we see that slower initial responses led to higher instantaneous reward rates, right? So the slower group, they were doing worse at the beginning, but they really did cross over with other guys. And that's also what we see in the model. And then finally, on the total reward point, it's just kind of the integral of that previous slide, but we didn't see the crossover point, but it looks like it might be on a trajectory to cross. And that's also what we see in the model. Okay, the final thing that we wanted to test, that's just verifying that the amount of time you spend looking at a stimulus is changing the learning speed. But we also wanted to understand, are the rats in some sense, or some circuits in their brains making sensible choices about when to slow down and when not to, based on whether they even can learn in the first place. So to get at this, we can compare what happens when you switch them to two new visible stimuli that they have to learn, or you place them in a setting where there's just nothing they can possibly learn. So we just present blank screens, okay? Now, in this setting, if they are sensitive to their learning prospects, then what you should see in the speed accuracy space is the following. When we switch them to new stimuli, their SNR drops and they move to a higher error rate. And then if there is something to learn, so it's a new visible stimulus, then the reaction time should go up, right? So you slow down to try to learn better, and then eventually you move over to this more optimal point. Whereas in the transparent stimulus case, there's nothing you can possibly learn. So actually the optimal thing to do is just fast guessing, go fast, right? So these make opposite predictions. And what we see in these animals is basically that. Here's a new visual stimulus. You can see they slow down again and then slightly speed up to get closer to optimal. Whereas for the transparent stimulus, we see them dropping towards fast guessing, and they end up responding faster than they do at the end of the learning group. So that seems like some evidence that maybe they're adopting a strategy that's sensitive to the learning prospects, and the model can recapitulate this as well. All right, so to summarize, I've shown you that rats seem to forego immediate reward. Maybe this is so that they learn faster and accrue greater total reward. I've shown you this simple model, which you can relate to a learning DDM to describe this trade-off. And I've shown some experiments where we started probing whether rats can adapt their behavior based on their learning prospects. And I just want to say, because it may seem like, well, is this really going to get us towards big AI systems that can do interesting things? So, we've got these incredible RL systems that can play Go and all of these things. But I do find it interesting that actually DeepMind applied these agents to this task, basically. So this was a random dot motion task, not actually visual object detection, but it's a task that requires solving the speed accuracy trade-off. And that these state-of-the-art agents fail on this task. So I think there is a lot more to learn about how to make agents that can flexibly learn all kinds of new tasks, not just AlphaGo or this task. And just to be clear, like these people would have no trouble modifying this algorithm to do this task tomorrow, right? But the point is they don't have one system that seems like it can do all of these things at the moment. So I'll just leave it there. I think the requirement to learn quickly is really demanding and may sculpt many aspects of behavior, and figuring out how we do this sort of cognitive control process that manages the learning process seems like a really avenue for the future. Acknowledge people who did this. Oops, I guess this is animated. We got, in particular, Javier Macis, who did all of these experiments, deeply involved in the theory, just did an incredible job with this project and funding. And I'm happy to take your questions. Thank you.